Pluto is a distant and perplexing minor planet. Once a member of our planetary family, consistent and unsettling claims by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking disclosure. They suggested that this chilly world is on a collision course with Neptune. But how could this happen, and what might be the consequences of such a significant event? Are we witnessing a startling effect caused by orbital instability, or is there more to this impending celestial encounter? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet, is unique due to its odd orbit. It remains a subject of interest and study in our vast cosmic neighborhood. Recent theories from leading experts suggest that Pluto's orbit is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising alarms about a possible hazardous collision between these two celestial bodies, which could pose a massive threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even completed one full revolution yet. The intrigue doesn't stop there. Pluto's orbit is marked by its unusual elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more extraordinary is its inclination of 17 degrees to the ecliptic plane. The path Pluto follows is far more extreme compared to other planets. One of the most fascinating aspects of Pluto's orbit is its intersection point with Neptune's. For at least 20 years in each orbit, Pluto generally moves closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers sought to determine its peculiar orbit. Unlike other planets whose orbits lie close to the ecliptic plane, Pluto's orbit stood out due to its steep inclination and warped shape. The mystery deepened with the confirmation that Pluto's orbit does indeed cross Neptune's. The investigation of Pluto's orbit, despite these complexities, showcases the intricacies of celestial mechanics. The three-body problem in space. Understanding how three bodies like Pluto, Neptune, and the Sun move and influence one another through gravity is notoriously complex. Pluto's orbit is, in fact, chaotic. Small deviations in initial conditions can lead to significant differences over long periods. However, these remarkable properties of Pluto's orbit have been found to maintain stability over extremely long timescales, keeping chaos at bay. Recent simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Jupiter's immense gravity is sufficient to keep Pluto on a stable path for potentially billions of years. These factors are crucial in maintaining order and stability in celestial mechanics. Without these forces, our solar system would be a far more chaotic and unstable place. Pluto's orbit is a striking example of celestial mechanics at work, demonstrating both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the complex and dynamic nature of space. Predicting major events, particularly those involving erratic orbits like Pluto's, presents enormous challenges. The inherent unpredictability of such systems means that long-term forecasts are often fraught with uncertainty. While numerical simulations provide a powerful tool for understanding and predicting the future behavior of celestial bodies, they also underscore the limits of our predictive capabilities. So, why are prominent astrophysicists suddenly voicing concerns about a potential collision between Pluto and Neptune? Despite the various complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in astrophysics, have expressed concern over a possible crash between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a dramatic and devastating event for our solar system. The impact would release a tremendous amount of energy, likely destroying Pluto due to its smaller size and icy composition. Debris from the collision could spread across the solar system, potentially posing a risk to other planets and their moons. For Neptune, such an impact could alter its atmosphere and possibly its orbit, depending on the details of the collision. Michio Kaku, a prominent theoretical physicist known for his work in string theory, brings an interesting perspective to the discussion. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics offer valuable insights into the mysteries of phenomena like Pluto's orbit. Understanding the intricate gravitational relationships and orbital mechanics of celestial bodies like Pluto can provide critical information for future space missions. This knowledge can help us explore the solar system more effectively, anticipate potential dangers, and even plan missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to the exploration of other celestial bodies, offering a guide to how we might approach and understand distant worlds. Regarding planetary science, celestial mechanics, and theoretical physics, these fields are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a spectacular event in astronomy, offering a mesmerizing, yet catastrophic glimpse into the dynamic nature of our solar system. Observational open door that may, as a matter of fact, interface with string hypothesis. String hypothesis, a theoretical system where point-like particles in molecule material science are supplanted by one-layered strings, endeavors to make sense of the major powers in issue in the universe. The effect could make outrageous circumstances of energy and gravity, possibly prompting conditions where expectations made by string hypothesis could turn into recognizable. For instance, the high-energy effect could give bits of knowledge into the conduct of key particles and powers under outrageous circumstances, a pivotal region of interest in string hypothesis. While the direct effect on Earth would be unimportant because of our separation from the external planetary group, the logical ramifications of such an occasion could be enormous, potentially adding to our comprehension of the crucial nature of the universe as portrayed by string hypothesis and different areas of hypothetical physical science. Pluto's particular dance around the Sun keeps on enchanting researchers and devotees the same, contributing a window into the complexities of sublime mechanics. While its renaming as a smaller person planet sparked conversation and reshaped our comprehension of planetary bodies, later disclosures about its circle have reignited interest in its job inside the close by planetary gathering. Neil deGrasse Tyson and Michio Kaku, two unmistakable voices in space science, have raised concerns about a potential effect between Pluto and Neptune, revealing insight into the complex powers at play in our vast neighborhood. Their admonitions highlight the significance of understanding the gravitational collaborations and orbital mechanics that administer the developments of divine bodies. Pluto's circle, set apart by its unconventionality and steep tendency, resists customary suppositions and difficulties our point of view on planetary movement. Not at all like the almost roundabout circles of its adjoining planets, Pluto's way follows a remarkable course, crossing Neptune's circle at focuses during its long excursion around the Sun. The gravitational impact of different planets, particularly Neptune, plays a huge job in shaping Pluto's circle and keeping up with its soundness over numerous years. Notwithstanding the turbulent nature of its way, Pluto's circle remains generally steady inside the more extensive setting of the planetary system's gravitational field. The potential for a crash among Pluto and Neptune, as recommended by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the continuous vulnerabilities and flightiness in planetary dynamics. While such an occasion stays speculative and exceptionally far-fetched in the close-to-term, the gravitational dance between Pluto and Neptune underscores the fragile equilibrium of powers that oversee divine bodies inside our nearby planet group. Past its logical importance, the investigation of Pluto offers reasonable experiences for future space investigation missions. NASA's New Horizons spacecraft, sent off in 2006, provided dumbfounding pictures and information of Pluto and its moons during its memorable flyby in 2015. The mission revealed astounding subtleties of Pluto's surface highlights, including tremendous fields of water ice and expansive plains of frozen nitrogen, enhancing how we might interpret the topographical cycles molding the far-off Bantam planet. The success of the New Horizons mission highlighted the innovative advances and cooperative endeavors vital for profound space investigation. By concentrating on Pluto and its moons, researchers acquired significant experiences into the variety of heavenly bodies and the ecological circumstances present in the external ranges of the planetary group. These disclosures have suggestions for future missions to investigate other Bantam planets and trans-Neptunian objects, helping us grasp planetary arrangement and development. Pluto's status as a Bantam planet has additionally started conversations about the measures used to characterize heavenly bodies inside the planetary group. The discussion over planetary arrangement reflects more extensive inquiries regarding logical scientific classification and the advancing idea of cosmic information. While Pluto meets a few rules for planetary status, such as circling the Sun and having adequate mass for self-gravity, its order as a Bantam planet features the variety of divine bodies past the customary 8 planets. Embracing Pluto's circle expands how we might interpret sublime mechanics and planetary dynamics to the external compasses of the nearby planet group. By examining the connections between Pluto, Neptune, and other divine bodies, researchers can acquire further bits of knowledge into the arrangement and development of planetary frameworks. These experiences are fundamental for developing hypotheses about the beginnings of our nearby planet group and understanding the cycles that shape planetary bodies over billions of years. Pluto's revelation and ensuing study have added to how we might interpret planetary movement and the improvement of the Kuiper Belt, a locale past Neptune populated by little frigid bodies. Analyzing Pluto's circle offers signs about the gravitational connections that might have impacted the arrangement of planets during the beginning phases of the solar system's advancement. Understanding the intricacies of celestial mechanics can additionally illuminate future space investigation missions, including the quest for habitable universes past our nearby planet group. By concentrating on the developments of far-off divine bodies, space researchers can distinguish potential focuses for future investigation and evaluate the achievability of heading out to other star frameworks. The expected effect of a Pluto-Neptune crash, while profoundly improbable, fills in as a sign of the powerful idea of the universe and the consistency of enormous-scale occasions. As we keep on investigating the external ranges of the planetary group and past, the investigation of planetary circles and celestial mechanics will stay a focal concentration for cosmologists and space organizations the same. Pluto's circle, which veers off essentially from the ways of different planets, offers important examples about the intricacies of planetary movement. The dependability of its circle over long time scales, in spite of its unusualness, gives significant bits of knowledge into the equilibrium of powers that administer the developments of divine bodies. It might be said that the continuous investigation of Pluto's circle and its expected communications with Neptune mirrors the more extensive difficulties of grasping the universe on the loose. With each new revelation and each hypothetical model, we proceed to refine our insight into the universe, uncovering the mysteries of far-off worlds.